We're showing a carry select adder. What's the basic concept? Basic concept is we're going to compute a carry and use that as a selection into a multiplexer of the next 4 bits. Right, we're going to use the lower 4 order bits, but while we're calculating the sum of those first 4 bits, we're also going to calculate the sum of the next 4 bits. But you're going to say, as we talked about last time, we can't calculate this sum until we have the carry coming in. So actually what we do is we calculate both cases and then just select the one we want once we figure out what that one is. Okay. So this uses redundant calculation of both cases. This would be just like you want to go get pizza, and you can order it, and you can wait for the order to come and then pick it up, or you can just, Little Caesars hot now. They have a pepperoni and cheese is already ready, right? So which one do you want? They don't know. They're going to make both. You come and select it. You don't have to wait. You don't have to wait for them to make it. You don't have to wait for them to cook the bits here. It's already baked. If you want it to go fast, you even waste energy. See? You're wasting energy. We know we're going to throw away half of these results. But why? Well, it gets done quick. That's up to the customer. It depends on the analysis. What is the right decision? There's some problems in the study set, giving you a chance to try each one of these different adder designs and do a little bit of design work with it, calculate propagation delay. So we're good on adders, including analysis and design. How about if you wanted to build a subtractor? This is, I think, very cool, and I always thought this was interesting when I saw it the first time, and I still respect it and think it's very elegant. This box can be any of the adder designs we looked at or other. There's actually many adder designs. I showed you the 3 most popular ones. But now we take an adder and make a subtractor. This is very cool. Is use the property that addition is the same as adding the negative of the second term. So a plus b is the same as a plus negative b. If I have a and b in registers, because these are RS and RT from the first slide of this module, they're sitting in registers, the 2 inputs I want to either add or subtract. If I want to subtract them, I'm going to complement the bits. Complement in this case is 2's complement, so actually inside this box will be complement plus 1. This is the functional complement, right? Then there's a switch box. What functional block is good for switch box? Mux. Okay, selecting many to 1, many to 1. So this switch will say if I'm doing a subtraction operation, I want to select this path where the B has been complemented. If I'm doing an addition operation, I want to select the uncomplemented and just put them both into the adder. So there's also overflow flag, which we'll talk about. So how would you design this using Boolean gates? So here's a very slick solution to this problem using an adder to implement a subtractor using 2's complement. It turns out what we have is our first ALU design. It's actually a very simple processor with 2 instructions. One instruction is add and the other is subtract. Go back to module 6. Remember, instructions were encoded as bits. We had a feel for op and func. Here we have a processor that has a single bit, is either add or subtract, and this is the guts of the processor. So we can take in A and B. If I want to add A and B, I set this line to 0. So what happens when I have 0 exclusive ORed with anything? Good question. 0 exclusive ORed with anything. Not 1. X exclusive OR with 0 is X. X exclusive OR with 0 is X. So here's X. X can be 0 or 1. What's 0 exclusive ORed with 0? What's 1 exclusive ORed with 0? What's the truth table for exclusive OR? 0, 0, 0, 1, 1, 0, 1, 1. This is A and B. This is A exclusive OR B. So exclusive OR is cookies or ice cream. So you can have nothing, you can have cookies, you can have ice cream, but you can't have both. This is exclusive OR. So if I exclusive OR 0 with 0, I get 0. Exclusive OR 1 with 0, I get 1. So this is x. X exclusive OR 0 is just itself. It doesn't change it. What's interesting, if I exclusive OR something with 1, what does it come out? X exclusive OR with 1 is, well, 0 exclusive OR with 1 is, all right, so that was not x, because I started with x is 0 and I got 1 out. Well, now I have 1 exclusive OR with 1 is not x. So we conclude something very useful when you're designing hardware. Exclusive OR gate is a selective complement function. It can either complement or not under hardware control. If you make the control line, which is the other thing you're XORing with, a 0, it's unchanged. If it's a 1, you've knotted it. It's a selective knot. If we want to add A and B sometimes, and sometimes we want to say A minus B, we can still use the same adder and say A plus a negative B. Well, how do we get negative B? We invert the bits, but it's 2's complement. What else do you have to do? Add 1. What's the coolness here about adding 1? How does it work?
Putting the carry in.
You got it. Ralph's got it. Tell me, speak up. He's looking at it right here. What's this about?
Yeah, if it's 0 and adding, it doesn't carry in anything. If it's subtracting, the XOR gates invert everything, and then the carry in of 1 makes the 2's complement.
So it's automatic with no extra work. Because we already have a carry input to this whole adder. Where do we see that one? It's actually here. All right. On all these designs, there's a carry in. If there's no carry in, which is the normal case, you just want to add A and B. You don't want to add A plus B plus 1. You just want to add A and B. You're going to set that to 0. But now it's coming in handy. Where's the handiness? Well, if it's subtract, I have to complement and add 1. So this line goes to 1 because I need the 1 function here for this conditional knot of XOR. And then what? No big deal, just connect it here too, and then boom, what? You've complemented and added 1. So if this line is set to subtract, it's a control line. See the data path? See the control path? It's only 1 bit control. Gives us 2 choices though, that's fine. We can add more bits. If it's a 1, I'm going to complement and add 1. So I do what here? If this control line, in this case, the control line is set to a 0, I compute A plus B, because that's why we call it an add not subtract control. Add not / subtract. So when this thing is a 0, it's doing the add. It means it's active low, because it's a not. When it's a 1, it's doing subtract. So if it's a 0, we want to do A plus B. Can anybody see the circuit computes A plus B? I see some nods going on. Suppose this control line is set to 1. It should compute A minus B. Yes, and Ralph's right. Because he used the adder to compute A plus negative B. Very cool. This is realized as A plus minus B. What's minus B? Since it's a 2's complement number, it's negated plus 1 to go from here to here. Negated plus 1. Make a multifunction. This is our first processor using bits to select the operation in the data path, selectively complementing bits of A and B to compute either the sum or the difference. We can then build more things around it, which we're going to do next, and show the fuller data path. I'll let you guys ask any questions on this. So data path in gold, control path in blue. This is ALU. In this case, this ALU only has, instead of how many functions can this ALU perform? 6 bits as a decimal value. 64, exactly. In our case, we just have 1 bit come in. It's 2 cases, add or subtract, and that's shown here. We already saw this on the previous slide. This is just redrawing this. But what I'm going to do now is connect this up, and now the light bulbs will start to go off. Module 6, we had all these bits of the instruction in the machine code. We had 6 bits, op, 5, 5, 5, 5, and 6. So the 6 bits of the func, if it's a register operation, like RS, RT, and RD, we're going to use the func field as 6 bits of input, and now here's using a decoder. What's the catchphrase for decoder? I drew it up here last time. Yeah, good. 1 hot output. You got it. So 1 hot. Decoder is 1 hot. What does that mean? It means that we're going to take these 6 bits of this func field, and we're going to put this into a 6 to 64 decoder. So 6 bits come in, 64 decoded bits come out. These are encoded as a binary number. This is lighting. We say it's lit. One line of this output will be lit. So if a 32 comes in, which is add, where did I get that? It's testing reference sheet, right? 32 add for func. If I want to do an add instruction, when the bits of 32 comes in, what does that look like? It's 6 bits. 32 looks like what? So it's 1 and then all zeros. Yeah, you got it. And then 34 is add and subtract. So basically, when this instruction is executed, these bits of this field are hardwired to a decoder. One of these lines is lit for each case, and then I can and or this in the data path to realize whatever operation I want to execute. This is very cool because it lets us design a processor from Boolean gates, taking the input and decoded it. So if it's an add, this line is hot. What am I going to do here? I'm going to only enable the output, and I'm going to talk about this in a second. But there's a lot of things connected to this where we're just doing an adder, but there's also a multiplier and a shift left logical and a whole bunch of things that can connect to RD. We're going to show you how you can connect these up using these tri-state buffers in a second. But add doesn't have to change any functionality. If you're doing an add, there's nothing else to input to the circuit. We're just going to add RS and RT. If you're doing a subtract, what do you need to do? If subtract, that's a 34. This is line number 34. If you count them, there's a dot, dot, dot here. But there's 0 up to line 32, 33, 34. If 34 is hot, it's lit, then I'm going to get a 1 here. So I put a 1 into all these gates, which means I inverted this and I added 1. Only when this func field is equal to 34. Why only? Because this is 1 hot. There's no other case where this line number 34 output is going to go to 1. When line 34 is 1, what are all other? 0. 63 is 0. So then I can use that in my circuit as 1s and 0s to AND in or to XOR in this case. So let me ask in the blue and the control path first before we talk about the data path. Any questions on how the func field relates to the design of the data path using a decoder? I gave you in the study set some more example, which we're going to look at another example in a second. And I'll give you some more in the study set to try. Given a decoder, build me some instructions. How? Here's the instruction definition sheet, just like a testing reference sheet. Now I want to add a new instruction. How do you do that? Well, first you set the bits, and then what? Put it through a decoder. Now you know that instruction is being executed. Then what do you do? Well, tune the logic. We show you some standard ways to do that. Of course, you can use K-maps, and we use design tools like Verilog, and then it will synthesize the actual gates. But a lot of times we use these types of approaches these are good things to know. Like if you want to make a conditional NOT, you can use XOR, okay? And that's what we have going on here, where we show you some of the basic approaches to design this. So I'll let you ask any question on control path. Can you see the connection between the bits of the instruction encoding and how it activates the circuit to compute? Okay, so now once we've got the output here, remember, as I said, this is an adder, which is doing addition and subtraction. What? Instructions. All right, this is for ADD, right? And then we had sub. Also ADDI and sub I. The only difference, we're going to take a constant here. Suppose this is ADDI. Well, what would you do here? You would take the op actually is going to come into here. Okay, and then you have 16 bits. That's going to be added over here as a constant. The 16 bits is going to come up here. ADDI. But remember, we have adder, we have shift left logical, we have a whole bunch of data path functions to build. Okay, how do we connect them together? One way to connect them together is on a bus. The catchphrase for bus is a bundle of wires. That's a bus. So what's the problem with just taking, let's say, the output of the adder and the output? So here's our bus. Let's call that RD bus, which is our data bus, is a destination, and we connect that to it. It's wired up, and we have a SLL hardware, right, in the data path, and it's connected up. And then we have, I don't know, a multiplier any instruction we want to, XOR or any instruction we want to build, okay. What's the problem with connecting these together as a bus? They interfere with each other. So in other words, this is a bundle of wires. How many wires? 32 in MIPS. This was 32, and this is 32. But let's just look at the lowest, least significant bit. So the least, if I zoom inside here, which is what I'm doing there in that diagram, I look inside, there is the output, let's just call it sum 0, and then sub 1 line, and so forth. This sum 0 is either going to be its Boolean, right? So it's either a 0 or 1, right? Suppose this thing is outputting a 0, and the output of this from this SLL, excuse me, multiplier, M0 bit, is a 1. See, suppose this is a 0, and suppose that line, M0, is a 1. Now you're going to connect a 0 and 1 together. What is that? It's a collision. It's indeterminate, right? There's a transistor in here trying to drive this to 1. And you're going to burn it. What you'll end up doing is you'll burn out the transistor eventually. This transistor is trying to make this line 1, but actually it's shorted to ground. So that transistor is shorted out, and it just keeps dumping current to try to make this a logic 1. You can't. So the point is this. Okay, point. We can never connect two outputs, never connect two Boolean outputs together. Why? Because it's a contradiction unless you can guarantee that they're always the same, right? If this guy's a 0, if the one input's a 0 and the other one's a 0, you can connect them together. There's no conflict. But if they can sometimes differ, it's saying that it has to be 0 volts. Another transistor is saying it has to be 1 volt or 1.2 volts. It's a wire. It does whatever the transistor says. The electrons follow, right? So there's a contradiction. It can't simultaneously be 1.2 volts and be 0 volts at the same time. So how does it decide? Actually, it doesn't decide. It's random. So that means actually it's a very bad thing. Sometimes your circuit may work, and sometimes it won't work. Okay, we don't like those kind of transient faults. Race conditions are very hard to test and get rid of. We always like to use a tri-state buffer. So what the tri-state buffer does is provides us 3 states, either a 0, a 1. We can use a tri-state buffer to get 3 states, a 0, a 1, or what's called high impedance. They use high Z. Okay. If you take a circuits class, what's the symbol for impedance? Z. So high Z is high impedance. What's impedance? Okay. So what's resistance in an electrical circuit? Is a resistance. Yeah, it's a resistive, is showing you a loss, right? So we have some energy, voltage applied, and some current will flow. Resistance is a ratio of those two, but it's basically telling you how much current you get out based on the potential energy you apply. So it's basically telling you the loss that occurs. That's resistance. When you have impedance, we had capacitance and inductance. Capacitance and inductance, the load, the generator feels that it has to provide extra energy, but the energy is returned to the circuit. So impedance is resistance plus, not added like this, but these are imaginary numbers, right? Capacitance and inductance, right? We use the letter L. So do you guys want a handy thing about, like a capacitance actually is a good one? Or you're good with this? You want a little handy thing? Okay. So my electronics teacher told me in high school, and it stuck with me all these years, resistance is real loss. It's gone as heat. You know, it's electrical energy, and we transformed it to heat. It's gone from the circuit. Capacitance is actually there, and you get it back at the end. So he gave this example. He made it. This is the day when we used to use paper money, right? Everybody came to class. He didn't say why. He had a really cool teaching approach. He'd always keep you interested. He said everybody had to put $1 on the table. He said that was a capacitor. We're storing some charge there, and at the end of the class, you got it back. So he said, in the end, was that capacitive loss? You're putting $1 here, and get it back later. It looks like I have to pay it at the time, but actually in the non-transient response, it's not a real energy loss. It's not real cost. It's not real cost for me to put $1 there if you're going to give it back to me at the end of class. That's what a capacitor does. It stores charge. So whenever you have a circuit in every circuit, right, we have capacitance, inductance, we have wires. Whenever we have wires, and we have capacitive effects. We have, remember the insulator and transistor, we had a silicon oxide. So these are capacitive effects, inductive effects. They're affecting impedance. Different than resistance. Resistance it's lost, it's gone. These things are actually better than resistance in some sense that they don't steal the energy from the circuit, but we have to deal with these nonetheless because at the time it's really deducting from the money you have in your pocket. So when we use high impedance here, what we're doing is in a Boolean circuit adding 3 states. 0 is logic, 0 is false, true, and this means no decision, no decide. Okay, high Z means I'm not talking. Okay, which is a funny thing too, is you go to some meetings and electrical engineers will ask a question, the guy doesn't answer, which is, or sometimes your professor asks a student a question and they just don't want to speak, because why? If they say anything 0 or 1, they're making their situation worse. So what do? High Z. You'll say like, oh, high Z. Okay, so if somebody asks you a question and they don't reply, your significant other, girlfriend, whatever, and just, oh, high Z output, I see. It's true. So why do we use it here? Well, we have all these devices now that can be generating, potentially talking with the register file. What do I mean? They're going to connect on a bus, which is all these bits of RD, okay? We can draw all of them and it gets confusing, right? So we just show you the first and then we go more. This S0 from the sum is going to be the same data bit that goes into the destination register as the output of the multiplier M0, as a P, actually, product, 0. We don't want to connect them together. We only want one at a time to drive. So actually what we're going to do is we're going to use this enable line. And here's the function of this tri-state buffer. Okay, so whenever we see this triangle, it's showing us, telling us what the circuit symbol does. Inputs goes to outputs. It's shooting bits just in this direction, but there's a gate, like a transistor we talked about. Okay, so tri-state buffer. Okay, the input data here will go to output data if and only if the enable is set to 1. So when do we want to enable the adder to talk to the RD register file? Only when we're adding or subtracting. That's the only time that we use this hardware for compute and output. There's going to be other times, right? I didn't draw all this because it's getting too much, right? But there's going to be other times the multiplier has an output that goes to RD, and other times SLL goes to RD, and other times shift right goes to RD. So who gets to talk so that we don't have this situation that one guy says a 0, another guy says a 1. You're going to say, well, why are they all computing these different things? Well, they may not be even computing. They're just sitting there. But do they sit there? Do they say a 0 or 1? Well, any choice they have is going to be wrong half the time. The only right choice that they could say is no comment, is high Z. So a little takeaway, this is like an example, but it's an example of a bigger thing to keep in mind. Anytime we design hardware that has an output, you're connecting 2 outputs together. Remember, always put in some tri-state buffer to enable exclusive control to write into that shared bit or shared channel or bus. This question?
You had your hand up first. Yeah. Does that enable, is that are those inverters, does the result of the addition or subtraction always invert? Is it always inverted?
Pointing to here or to here or to here?
Enable.
Enable?
Yeah, are those inverters?
No.
No? Those are just pass-through?
That's just pass-through.
Oh, okay.
Yeah. Right. Inverter.
Oh, right.
Bubble always means invert. This just means drive A to B. Now the interesting thing is you say if it's A input to output, this is A to not A because there's a bubble. But then you're going to say, well, why do you need this? Because this is electrically isolated. The electrons that are on this side of the triangle are not the same electrons that are over on this side of the triangle. What does that mean? It's electrically isolated. There's different ways to do this. You can do opto-isolated. What they actually do is they convert it to light, and they use a photodiode to convert back to electric on the other side. Okay. So the 7400 series are chips that you can hold in your hand. They're actually TTL logic levels. So a 0 is 0 volts, a 1 is 5 volts. But a lot of interfacing devices need that voltage to work. You want to connect up your microprocessor to something to turn lights on or off, or control things. You can use this to drive that device. So you can take in inputs here. As you can see, these inputs are connected in this way, and here's the control, is direction. This can either go from A to B or B to A, and what they do is they just have tri-state buffer for each case, and they have logic to turn on one of the two and to enable this, and the enable line is here. So this is a real chip you buy, or you can build this on an integrated circuit. It's a module in Verilog. You insert this in your circuit anytime you want to interface to the bus. We provide a voltage here, but the electrons don't flow across. This way we never get this short condition of 0 connected to a 1. Actually generate a new signal. So remember, every time we have a triangle, it's a buffer function. Buffer means input equals output unless we have a bubble. Bubble is always inversion. So let's generate some control signals. We generate the data path using the tri-state buffer. What about generating some control signals? We said control signals from this box. One is overflow. If I try to add two numbers together and the result doesn't fit in the number of bits I have, it's overflow. So overflow condition basically is saying that the carry into the most significant bit does not equal the carry out of the most significant bit. There's a proof in the book for this. It's a little bit long, but the basic idea is saying that I can XOR together the most significant bit of carry in, the most significant bit of carry out. Here's the same circuit we just saw. Don't let this throw you for a loop. How does this relate to the RCA adder? Same or different? And if it's the same, why? It's same, and why? This is just drawing it this way. It's not to mess you up, it's just maybe it fit on the page. So here's the same ripple carry. We can take carry in of the most significant bit. This is a 4-bit adder, as we can see, right? There's 4 bits total, 0 through 3. Carry in and carry out XOR together. That is the overflow signal. What is this? If this is a 1 as a carry, I don't get a carry out, I must have overflowed. So overflow is 1, means there was an overflow. Why? Because I can't represent the carry in condition and A and B is 1 with the carry out of 1. We'll put some numbers. We'll do it in binary and decimal because it's good practice and also makes it totally clear. So you're given in this example, let A and B equal some number. So A is a binary number, and that is 0, 1, 1, 0. And here's 1, 1, 0, 1 is B. So this is base 2. So what is this number in decimal? Now, this is a 4-bit adder, and what we're working with here is, in this whole modulus, we're using 2's complement representation. So what is this number in decimal? 6. And what about this? But careful, because it's 2's complement, is this a positive or negative number? Negative. It's a negative number. So one way to take this, right, is to invert all the bits and add 1 is 3. So this is inverting, adding 1. This means it's negative 3 because it's made it negative. Here's the negative part, and the number is 3. What's another way to do this without doing any calculations? So this is negative 1. As 2's complement, 4 bits, 2's complement, negative 1. What's negative 2? 1 less 1 than negative 1, which is?
1, 1, 1, 0.
You got it. What would negative 3 be? 1 less 1 than that. Well, you can't take any 1s from here, so what do? You take 1 from the 2's, which means you took 1, 2, and then what do you have left over? All right. So this should be minus 3. So now I want to add 6 and minus 3. I can do that without overflow, no worries. I can do it in decimal over here. What's 6 plus minus 3? 3. Let's do it in binary. It's binary digits. It's actually regular math. There's nothing different. Regular addition. So what's 0 and 1? Okay. 1 and 0. 1 and 1 is 2. That's how we write 2, because we can't write a 2. And then what's 1 and 1? But this is 3. This is base 2 is 3 base 10. So 6 plus minus 3 is 3. However, suppose I gave you 7 plus 5. And these are 2's complement numbers, right? This is 7. Everybody sees the 7. Everybody sees the 5. Add it together. 1 plus 1 is 2. That's 2. Oh, wow. That's 3. And we're done, right? So what number is that? 2's complement. So what is this? A negative number or a positive number? It's a negative number. We overflowed, see? See, means we're overflowing. This is why it's into the MSB, and this is the sign bit. It has a special purpose. Is this the uppermost bit, most significant bit of any adder? If it's 4 bits, 32 bits, most significant bit is always keeping track of the sign. If you carry into the sign bit, game over, overflow. So let's look at this. What number is this? -4. This is -4. So 7 plus 5, we know in real life, is 12, base 10. It's not -4. So what went wrong? We overflowed. It's a condition. Overflow occurred. This means that this number is not valid. It means that the hardware we have cannot use this representation of 2's complement, which we don't have a choice to change that because all the data is loaded in memory and all the registers are loaded with 2's complement values because that's what every computer uses, 2's complement. So now overflow occurred. We have to do something. We either tell the user, repeat this with a different set of hardware, or we say that there's error, overflow occurs. There's no operation that can change the sign. Think of it. If you're adding 2 negative numbers, answer is a negative number. If you're adding 2 positive numbers, the answer has to be a positive number. We can never change the sign. But when we overflow, we're carrying into the sign. This is a logic circuit that will allow us to test for that. Yes?
So assume then that all addition is using 2's complement?
Actually, the entire processor uses 2's complement. Unless we tell you, I mean, sometimes we have you practice other ways, but then in the real world, it's 2's complement. Default is 2's complement representation, unless we tell you otherwise on the circuits. Suppose we remember we designed a branch function before. We want to branch if it's 0. How do you tell if it's 0? Well, here's some coolness, okay? You want to do 0 detection logic. One way to do this is to take A and B, all right? And one thing I can do is I can subtract them, and if I get a 0 result, then how is A related to B? Is A equal to B, less than B, greater than B? Let me say it one more time. I've already built an adder, right? And I built an adder and made it into a subtractor, so now I have a subtractor. So if I take A minus B, if that result is a 0, what does it tell me about A versus B? Is A equals to B? Double equals, actually. Thank you for reminding me. Double equals. Pretty cool. Suppose this number is, let's say, greater than 0. How does A relate to B?
A is not greater than B.
A is greater than B. How about we get a number that's negative?
A less than B.
A is less than B, or B is greater than A.